Good morning. This is Krishna Ananthony from Stantec. It gives me great pleasure to introduce Jeff Weller, also from Stantec. Jeff has worked for North Carolina DOT for 11 years and last 5 years has been working with Stantec. He's going to talk about indirect left turn movements at intersections. But I asked Jeff for a fun fact and he says, about himself. I says when he's not serving as a butler, tutor, chauffeur, chef, moderator, father to his two beautiful kids, he loves to binge on a variety of TV shows and movies. So here's Jeff. Take it away, Jeff.
Thank you, Krishna, for that wonderful introduction. So usually in this time slot, I'm trying to get presentations done so everybody can get to the lunch line, but with this new version of conference, everybody's on their own. So, but with that, I'm here to talk today about indirect lefts. Are they right for you? There we go. Today's topics: what exactly are indirect lefts? How can they work for you? How can they work? Where have they been implemented so far? What are some considerations for implementing indirect left intersections? And what are other ways indirect lefts can be applied? So what are indirect lefts? There's a lot of names for intersections out there that include indirect lefts, some of which you may have heard of, some you may not have heard of. The restricted crossing U-turn or the R-cut intersections, median U-turn or MUT intersections, J-turns, super streets, Michigan lefts, green T intersections, quadrant intersections. Some states call them synchronized streets. With every state and a lot of different agencies having the option to call them what they will, there's been a big push over recent years to kind of label these as RCIs, which is the reduced conflict intersection. So now I can change the topics to include RCIs, as now that you know what exactly that acronym means. So let's dig into how they work. So indirect lefts, one or more vehicular, or RCI, excuse me, one or more vehicular movements is or are redirected to a different path that results in fewer conflict points. Generally, it's the minor street that has movements redirected. Fairly straightforward, right? So the figure at the top shows the path of the vehicle turning left from the minor's approach the side street at a conventional intersection. The vehicle crosses over what we'll call the eastbound approach in this example and continues its path onto the westbound lanes. For an unsignalized intersection, this could happen as a two-stage crossing, where the vehicle pauses in the middle, or if there are simultaneous gaps in the eastbound and westbound traffic, the driver can make this movement as a single pass. With the RCI shown here, also known as the R-cut, J-turn, or super street, the vehicle turns right, utilizes a downstream U-turn, and proceeds westbound as shown in the middle figure, or makes the U-turn and turns right to head northbound as shown in the bottom figure. Now, with the earliest concept of the R-cut introduced in the 1980s, there were no direct left turns from the main line to the side street. Only the signal with the arterial, So the only signal with the arterial encountered was at the U-turn upstream of the side street. The industry standard, however, is the configuration shown here, which includes the direct left turns from the main line onto the side street. RCIs are best suited for suburban and rural areas where there's relatively low traffic volumes entering from the side street. I put an emphasis on relatively low because we've incorporated these types of intersections in many locations where the side street volumes may be equal to or higher than other arterials in the area. Here we see a breakdown of conflict points at a conventional or full movement intersection. You'll notice each leg has two merging and two diverging conflict points. The solid green and the half white, half red circles. In the middle of the intersection adds another 16 conflict points for a grand total of 32. It's important to point out that the category, here you'll see, that with an R-cut, we've reduced the conflict points down to 14. It's important to point out the category of vehicle-to-vehicle conflicts with the greatest reduction is the crossing conflicts. These conflicts tend to be the most severe in nature and are most likely to result in injuries or fatalities. The conventional or full movement intersection has 16 crossing conflict points, while the RCI example shown here only has 2. So this figure summarizes the past few slides about conflict points and also introduces the median U-turn intersection for comparison. This intersection is in its truest form. There are some intersections in Tucson, Oracle and Ina, and along Grant Boulevard that still allow the mainline left turns in addition to the through and right turn movements for all approaches. This has a reduction of conflict points compared to conventional intersections, but not as great as the 2 alternatives shown here. So safety is a large component of why there's been an increase in RCI installations over the past 10 to 15 years. But we should also discuss the operations of these intersections. RCIs have been shown to reduce delay and increase capacity, both for signalized intersections and unsignalized intersections. Let's look at how this is achieved for signalized intersections. So going back to basics for a second, for signalized intersections, a cycle is the length of time the intersection takes to call or service all phases. The phase is described as all traffic movements that are assigned simultaneous green time. On the left side, phasing diagrams are shown for simple intersections which consist of 2 or 3 phases. For a 2-phase signal, either the mainline movements, left through or right, are permitted to move, or the side street movements are permitted. Let's say that same intersection is now modified so that the eastbound left turn is given a protected movement and has a green arrow for part of the cycle. By protecting that eastbound left turn, another phase has been added. Now think about the 8-phase signal shown in the diagram on the right. That consists of giving the mainline left turns a green arrow and a protected movement. Once that phase is served, the mainline through and right movements are then permitted to proceed. This is usually the longest phase of the cycle, since the mainline through movement typically has the highest volume. Following the mainline phases, the side street left turns then get a green arrow, and the side street throughs and rights get their phase. Bottom line, there's a lot that happens at that intersection when the volumes are high enough that fewer simultaneous movements can occur, or the geometry of the intersection doesn't allow for certain simultaneous movements. So what does all that mean? So the solid colors here show the amount of time per cycle afforded to the mainline through movement per cycle. Remember, since that is typically the movement with the highest volume, it has the greatest impact on the efficiency and operations of the intersection. With each phase having yellow time and red time, every additional phase removes more of the available cycle length pie that can be given to the mainline. For example, if a motorist is stopped at a 2-phase signal, then the wait time is fairly short because only one other phase has to cycle through the intersection before the right-of-way returns to the waiting motorist. The available green time that the intersection receives is divided only between the 2 phases. So green time remains greater than the time the motorist is stopped and waiting. The same philosophy holds for a 3-phase signal. Even though there is an additional phase to protect left-turning vehicles, the wait time is still reasonable with only 2 other phases cycling through the intersection. Green time is reduced slightly, and the time the motorist spends waiting is about equal to the time the motorist is given to progress through the intersection. Therefore, 2- and 3-phase signals are very effective for maintaining traffic flow and reducing travel time. However, when traffic volumes increase and the number of lanes required to safely move through the intersection exceeds the capacity of 2- and 3-phase signals, more phases must be added. Specifically, left turn movements must be isolated and protected from oncoming traffic. Hence, the more phases that are added, the more time the motorist spends waiting for the additional phases to cycle through. When operation of an 8-phase signal is warranted, delay for the motorist is much longer, available green time is significantly less, and driver frustration begins to increase. Engineers reach for tools like RCIs when even 8-phase traffic signals cannot effectively manage driver demands on the roadway system. By incorporating signals with a reduced number of phases, the capacity of the roadway is increased significantly. I want to revisit this slide and tell you one of the best analogies I've ever heard for redirected lefts. Imagine you're at the grocery store and the only lane is open, only one lane is open at the checkout, even though it's very busy. This open lane is right next to the only exit. The store finally opens another checkout lane and it's all the way at the other side of the store and the furthest away from the exit. But there's no line. By heading down to another cashier where there's no wait, getting checked out, and walking all the way back to the exit, You're likely leaving the store faster than everyone who is waiting in the one line because of the shorter distance to the exit. At a conventional signal, the amount of green time given to the side street is very low. So when the demand is high, those motorists are likely having to wait through more than one cycle. When we can reduce the number of phases, however, the effective green time is greatly increased. So now that we've covered what are indirect lefts and how RCIs work, let's take a look at where RCIs have been implemented so far. So there's at least 17 states that have incorporated some form of an RCI, be it the median U-turn, Michigan lefts, R-cuts, super streets, etc. I guess as there are far more states that have implemented at least one of these intersections with redirected movements. Unfortunately, it's difficult to keep a national inventory of all these locations. So what are some considerations when implementing RCIs? So there's not one type of intersection that accommodates all situations. I'm glad that there isn't, otherwise my job would be boring. Similarly, there's not just one solution for any intersection situation. I say that with a grain of salt because there are other factors to consider. Generally, available space and funding are two of the biggest factors. So let's take a look at this example of an unsignalized RCI. Particularly in rural areas, unsignalized RCIs can be great countermeasures for various crash types. They avoid the need for signal and can be installed in an isolated fashion. So with unsignalized RCIs, studies have shown a great reduction in a number of, well, in all crash types, but a great reduction in certain ones. So as you'll see highlighted here in orange, total crash types, fatal and injury crash types, angle and right turn crash types, and left turn crash types all have this statistically significant reduction in crashes, anywhere from 46 to 75% reduction, which is pretty much, is pretty astonishing. So these data are courtesy of a research project on behalf of the North Carolina Department of Transportation that examined the benefits and capacities of RCIs. Some people say, aren't U-turns unsafe though? The reality is that U-turns are not a major safety concern. The perception that U-turns are dangerous may come from downtown areas which have signs banning U-turns. In those areas, the roadway is tight, and a U-turn maneuver may cause problems with traffic flow, especially if a vehicle's turning radius doesn't allow the movement to be made without backing up in the middle of the turn. However, national and local studies, including this one, have shown that U-turns are no more dangerous than normal turns from median divided roadways. Super streets, or RCIs, are designed to accommodate U-turns at appropriate locations. So now let's talk about signalized RCI corridors. So signalized RCIs have the best chance to realize their true operational potential and efficiency when part of a corridor with a coordinated signal system. By having a coordinated, using corridor and coordinated right next to each other is fun. By having a coordinated signal system where there's communication between signals, platoons of vehicles are able to traverse the corridor, generally only having to stop at one or two signals. The progression of the signals can allow the downstream signals to turn green as the platoon is approaching. This is part of how overall travel times are reduced. Coordinating 2- and 3-phase signals is a far easier task than trying to coordinate successive 8-phase signals. So use this graphic to show you that in theory, the two directions of an RCI corridor operate as independent facilities. The green circles represent the signals that the eastbound through traffic would interact with, while the orange circles represent the signals the westbound through traffic would interact with. Now, if there wasn't enough storage for the left turns or U-turns and they're spilled back to the main line, that would certainly affect the independent operations. In this situation, if this situation were to exist, field adjustments could be made to the signals, or if there's available room, the storage could be increased. So I had our first question, which we'll go ahead and answer. Bill F. asked, I think you mentioned RCIs are best in rural and suburban locations. Is that because more right-of-way is typically required? Generally, I mean, that is certainly a part of it. When we are starting with designs of RCIs, typically it's going to be with, you know, the starting point before we do any reductions is generally a 46-foot median and then two 12-foot lanes. And then depending if you need, if you only need a single U-turn instead of 2 lanes for the U-turn, then you can begin to shrink down median width. The other thing about why suburban and rural locations is you're generally going to have less traffic on the side streets. So the ratio of traffic, the traffic movements, especially your left turns either onto the side streets or from the side streets, is another determining factor. But thank you for that question, Bill. So now I've got a little firsthand video. It's an account of a newly opened RCI corridor a few years back. It was also one of the first RCI corridors in the area. So it was a new concept to most of the drivers. So we'll get through the first little part and just enjoy the scenery of I think that was shot in the spring a few years back. So like I said, it's still under construction. So as we come up to the first set of mast arms, you'll notice that there are no signals on there, as that wasn't part of the first phase of the operations. But as we approach the first signal, you'll notice that this platoon of vehicles jumping the gun. Apparently thought it was faster than it was. So you can keep judging some drivers as we go through and look at the nice scenery. Okay, now we'll get back to it. As we're approaching the first signal, you'll notice that this platoon of vehicles gets stopped while the opposing left turn has the right of way. Then you probably couldn't see when the light had turned red, but it wasn't red for very long. That's part of the beauty of having the two-phase signals. So now as we get going again and get through the green signal, you look ahead and it is a progression of signals. But you'll notice that as we get to the next signal, which is the U-turn, coming the opposite direction, that signal is already green. So this platoon of vehicles is able to keep moving through. Excuse me. As we approach the third signal, which is where the side street is located, and there's the leftovers or direct lefts, you notice that this platoon of vehicles starts to slow down as it joins up with the platoon of vehicles that was stopped at the red light. The good thing is, there's a slowdown, but there's no stopping, and that's part of a good sign of good coordination and good progression through the corridor. As we're going along, you see that there's another signalized U-turn movement that we're coming through, and getting back to speed. Like I said, this is newly open, so there were still some getting used to, or the drivers getting used to exactly how everything was working and the speeds. But you notice that we made it through that last signal, or the last two signals green. So it was only that first one you had to stop at, and then it was coordinated such that you're able to progress through. So we got through those signals, and as we start heading up the hill, you'll notice that the queue is starting to build. At the top of the hill is a conventional signalized intersection, and it takes a long time to ascend the hill and get through the signal. Or excuse me, it took as long to ascend the hill and get through that signal as it took to go through the entire RCI corridor. So that full movement ended up having such detrimental impacts on the operations of the corridor that a conversion was finally approved. Remember when I said there wasn't a single solution for all intersections? Well, this intersection that was a logjam had a large residential community and a school located along one of the side streets. With this heavy side street left turn movement, there's hesitation about redirecting that large of a volume to a U-turn. What ended up being the final decision was what was known at the time as a reverse RCI. With this reverse RCI, the side streets are provided direct left instead of the main line, Mainline lefts and side street through movements utilize the U-turn bulbs on either side of the intersection. For reference, the hill from the video is to the left of the screen, and the school and the residential are to the bottom of the screen. So this signal operates with three phases: the main line through, the side street left, and the side street right. Whenever we take RCIs to the public, everybody always asks, what about trucks? And what about buses? How do they maneuver? Can they fit in there? All questions like that. As you can see in this picture, there's additional pavement, also known as a U-turn bulb, that helps to accommodate larger vehicles. This low boy carrying the excavator is doing just fine making it through that with the, like I said, with the additional pavement put on for that bulb. And other people like to ask, can RCIs accommodate pedestrians and bicycles? For pedestrian accommodations, you notice the Z pattern in the figure on the left. Having the crossing utilize left turn channelization island also provides pedestrian refuge. For bicyclists, providing a cut through on the channelization island allows for crossing without having to navigate a curb. And additionally, for bicyclists in the lane, bike loops can be utilized at signals that include some form of actuation. So people also often ask about, what about illegal left turns? So the easiest method for preventing illegal left turns is with raised channelization. The picture on the right is from the intersection of North Oracle and West Ina in Tucson. With the allowance of the side street through movement and the mainline left turns, there's no realistic method of physical channelization. In the situation on the left, channelization for the mainline left turns acts as physical guidance to help prevent drivers from making illegal movements. Now, I know with this situation on the right with Oracle and West Ina, that it's two arterials intersecting. So with a situation like that, very well could be worthwhile to be looking at other types of intersections that may allow for more movements, but still operate more efficiently than just removing the left turns from Ina. So what are some other ways that RCIs can be applied? So you can use roundabouts for the U-turns. If you are in an area that has those, and if you have a road that generally single lane, but we've been installing 2-lane roundabouts at on 4-lane roadways also. There's also the concept of a roundabout corridor to where you have periodically spaced roundabouts, which don't necessarily have to be at a particular side street. They certainly can, but then all of your access in the middle, driveways or other accesses, or even roads, are what we call right in, right out, and they just utilize the roundabouts on either side of them for their left turn movements. You can also incorporate RCIs as part of interchanges. So let's take a look at a couple scenarios of that. So this interchange utilizes U-turns on the arterial to accommodate the redirected left turns, both from the freeway and from the arterial. Notice that this is based on the basic version, the original basic version of the R-cut that's from the 80s, to where there's no direct left turns. Now, a little more complex than that is this concept, which utilizes the time that the arterial through movement is stopped to both allow the motorists from the ramp onto the arterial and the eventual arterial left turns onto the freeway to cross over and be away from the influence of the arterial through movement. With this setup, and by coordinating a number of two-phase signals, this interchange both becomes more efficient as well as increases the safety of the interchange. I will note that I'm a big believer in alternative intersections and interchanges, so I will do my best to not talk about those too much unless we get a bunch of questions about them. So let's show the next generation how to think outside the box and improve the future mobility for generations to come. If there's any questions now, I'll be glad to answer them. While I still have time, I'll also be at the virtual stand take booth at 12:30.
Thanks, Jeff. That was a good presentation. Just waiting for more questions.
I'm so used to having little dots to show when somebody's typing. Keep waiting to see that.
I can ask you, you working on any exciting projects like these right now?
Yeah, so yeah, things where just got a message that don't have any other questions, but yeah, so things are a little bit slow in my area, but we always seem to have something going on with alternative intersections and interchanges. So right now, we're working on a pursuit in Florida and looking at basically combining a few different interchange types into one to try and solve this issue that's part of a design build in Orlando. So there's lots of options out there, and um, you, nobody should ever be afraid to, like I said, think outside the box and say, all right, well, how can we get cars from one place to another? Trying to go through either an intersection or an interchange, and say, all right, well, if it's going to be a little more distance, but it's going to be quicker travel time, then people will generally get used to that. So,
Right.
ooh, so Steve O asks, did you evaluate any other types of alternative left turn configurations? So it's kind of a wide open question, Steve. Yes, in yeah in my history, I have been uh, evaluating a number of intersections. We have begun to be looking at um, CFIs, which are the continuous flow intersections. For anybody that isn't aware of that, we also looked at some versions of contraflow and displaced lefts. So there's a wide range of tools in the toolbox that we get to use, and sometimes it's some hybrid of something else where we took um, a contraflow and essentially did what we call the double contraflow and did a grade separation with it. So it almost acted like quadrant intersections, but displaced left turns in the middle. So it was very interesting. So the short answer is yes. I have looked at a number of additional intersection configurations with redirected or indirect lefts. James G writes, what guidance is used to start looking at potentially changing the intersection layouts? So I know the leaders or the forerunners of RCIs in general have been NC DOT, Minnesota DOT has a guide that was produced, I think, 3 years ago. North Carolina Department of Transportation has guidance going back to I think around 2008, 2009, and then they had all these studies that followed thereafter. Um, so, but guidance is, first off, you want to make sure that with your traffic patterns, you'll want to do an analysis to make sure that it can be handled, and then you can start looking at the layouts and get the geometry and the roadway engineers involved. Certainly, James, if you want some more information, come find me in the booth, because it's more likely that I can get some links to you that way. But as you go through, you can do FHWA. It's kind of their website's dry at times, but they do have an alternative intersection interchange guide. I think it's at AIIG, and they can go through, and it shows it dates back many years, but it can show you a lot of concepts that have not been in place, that have not been put in place, but also many that have. It can give you some options about, or give you some ideas about what locations are good for those. Yeah, certainly, find me in the booth if you can, and I'll try to get you hooked up with a couple links for that. Can indirect lefts, this is Eunice, can indirect lefts be incorporated into 6-way intersections? I'm trying to think if I have seen many 6-way intersections. The short answer is yes. Without visualizing one of them by, you may have to figure out the best approaches, the best legs to have, downstream U-turns or some other way for connectivity. It can almost work like a jug handle, which we don't really do here. I think, New Jersey is the home of the jug handle. But there's certainly options. The best thing to do is, the best thing I find to do is have a printout of your intersections or draw a sketch, and then just start, filling with pen and paper, and say, all right, well, if road 1, if the cars need to go left from road 1 to road 5, what are the different ways they can do that? And you go through and iteratively figure out a combination that will work for for everything. John N. How do these compare to signalized roundabouts? So I will admit that I don't have much experience with signalized roundabouts. It has been, I know there have been some ideas for pilot programs in this area. I would like to think that signalized roundabouts would be able to perform, or these would perform on par, if not better. The thing about these is, the things about RCIs is that, like I was showing you with the with the signalized version, excuse me, is that when you can coordinate the entire direction of flow, it really lets you decrease travel time for that major movement, which is the mainline throughs. Signalized roundabouts, again, being a little bit of a novice in that area, I don't know exactly how they can, or how efficient they are coordinating with up and downstream intersections, or with other signalized roundabouts. Are there any CMFs for RCI or other left turn configurations? Just a follow up from Steve. Yes, there are. I should be able to get my hands on that. So, like I was saying, that with NCDOT being one of the forerunners in this field, they have a large traffic safety evaluation group. So between them and ITRI, which is the Institute for Transportation Research and Engineering, which is part of NC State University, the two of them do a number of projects together. Also, one of the long story short, professors at NC State is now working for DOT, and he has done presentations on the CMFs. So yes, again, find me, Steve, find me in the booth. Should be there around 12:30, and by then I will see if I have a link for those CMFs, or at least have somebody for you to get in touch with to get that information. my wonderful producer, Ben, has let me know that there are 10 minutes left. Like I said, if you don't get to your question now, or if you don't think about it until later on, I'm at the booth and at 12:30, and you should be able to get my contact information from my profile, and we should be good to go.
Thanks for a good presentation, Jeff.
All right.
Thanks for answering the questions.
Yep. Thanks, everybody.